All right, everybody, we're going to go ahead and get started. Thank you, everybody, for being here for our last Science on Tap of the year. We will get started with these again. Yes, we will get started again with these in the fall. But thank you so much for being here. My name is Cinnamon Moffett, and I'm the Research Program Manager here at Oregon State University's Hatfield Marine Science Center. This is a hybrid event, so we have folks that are online and in the room. So welcome to you all. Wanted to just let folks know that are online, if you have any technical issues, Roseanne is here in the room and she is monitoring. So if you have any of those questions, feel free to put them in chat and she will let me know if you're having any issues with hearing us or seeing anything. So feel free to use the chat and talk to us that way. For folks that are online, just to know your screens, share and mics have been turned off. So the only thing you have is that chat function, but please ask any questions related to the talk using that chat function, and we will get to those at the end of the talk. For those folks in the room, in order for this to be a truly hybrid event, to ask questions and for everybody to be able to hear, you will need a mic. So all you need to do if you have a question is raise your hand at the end of the presentation and I'll bring you a mic, or you can go to the mic stand right there and you can ask your question that way. But please just give me a little bit of time. I'll get to you and get a mic so that folks online can hear as well. Wanted to just let folks know that we are recording this event. So if you are interested in watching it again or sharing it with others, you can go to the HMSC or Hatfield Marine Science Center webpage. Scroll to the bottom of the event. Bottom of that page, there'll be a whole bunch of other events that you can see there, or you can go to our past seminar page and you'll find the recording for this event. The reason you are all here is to learn a little bit more about some of the tsunami mapping efforts that have been going on. So I would be amiss if I didn't tell you, if there was a tsunami right now, we would exit out these doors, which are behind this curtain, and we go up the ramp to the top of this building. So just throwing that in there because it's the right audience to talk about it. For all of you, I wanted to introduce tonight's speaker. We are just thrilled to have Dr. Jonathan Allan here to talk to us about his work. And I just want to do a quick introduction of John. So Jonathan Allan is a coastal geomorphologist with Oregon Department of Geology and Mineral Industries, otherwise known as DOGAMI. Allan completed his undergraduate and postgraduate degrees in New Zealand, specializing in coastal processes and hazards. Dr. Allan moved to Corvallis, Oregon, to take up a postdoctoral position at Oregon State University in 1999 and joined DOGAMI in late 2001. During the past 22 years, Allan has undertaken studies that include coastal erosion hazard mapping, analysis of the North Pacific climate, wave climate, and extent of extreme storms in the Pacific Northwest beaches. And in 2015, Dr. Allan took over the Tsunami program from Dr. George Priest after his retirement from DOGAMI. With the completion of the Tsunami Inundation Modeling for Oregon's coast in 2013, the Tsunami program has largely focused on Tsunami Evacuation Modeling, which provides improved understanding of the time and speed it takes for the public to evacuate along every route in the coastal communities. And we are just thrilled for Dr. Allan to be here with us and to talk about the work that he's been doing and some of the new modeling efforts. So I'm going to hand it off and have you go live.
Thank you, Cinnamon. Everyone can hear me okay? All right, perfect. So I thank you again for the opportunity to come and speak before you all this evening about Cascadia, and obviously a topic that probably many folks are familiar with in regards to the potential for a major earthquake leading to a catastrophic tsunami. So if you don't already know, my agency, Oregon Department of Geology and Mineral Industry, is the State Geologic Survey. We have a staff of about 35 people. We have sort of two programs, one focused on geologic hazards and geologic mapping, and then another program focused on mine land reclamation. And so we have a long history in the state of Oregon going back to the early 1930s. And over that long time frame, we've done, as an agency, a tremendous amount of work looking at geologic hazards around the state of Oregon. And obviously, in the last 2.5 decades or so, one of the major focal points for this agency has been addressing issues related to a Cascadia event and the accompanying tsunami. So what I'm going to speak to this evening is really provide you with some background information that kind of sets the stage for how we got to where we are today with the maps that we have. And so there'll be some background information about the geologic, the underlying geologic data that went into the ultimately developing these new numerical models and inundation maps for the state of Oregon. I'll then sort of switch gears a little bit and speak to our focus in the last, really the last decade, which has been a shift towards more trying to better understand how long it takes for people to get out of the inundation zone, as well as performing risk assessments up and down the coast, because that's obviously information that our coastal planners and emergency managers really need in order to develop their pre and post disaster plans. So minutes count, literally, when it comes to Cascadia, from the start or the onset of the earthquake shaking to obviously the time in which it takes for the waves to arrive on the coast and then fully inundate the coastline. And so I'll speak to that over the course of the next 40 minutes. So I wanted to point out on the slide up here, on the left is an image that I'm sure many people have seen over the years of the impacts of the 2011 Tohoku, Japan tsunami and the degree of destruction that occurred in that event. That was a magnitude 9 event. The image on the right is actually a product of some of our tsunami inundation mapping, and it actually highlights essentially 4 inundation zones, including in green, obviously high ground or safety. So the area in purple is what we define as our medium scenario. It's about a magnitude 8.9. So it's still it's a very big event. And it's very comparable in terms of magnitude, obviously, to Tohoku. And so looking at these side-by-side images, you kind of get a sense then of the degree of destruction that could occur in our coastal communities. And so obviously a major focal point for us is to really try to convey an understanding of both the science, but also obviously another critical part is developing the necessary outreach to build people's awareness. So the work that we do is largely funded through federal support via the National Weather Service of NOAA through a program called the National Tsunami Hazard Mitigation Program. And it's been going on now for essentially about 2.5 decades. It really began in its infancy in the early 1990s. And so this graphic here really highlights the sort of 2 elements to the work that we do. I work collaboratively on the science side with many other researchers in the Northwest and elsewhere. And then obviously on the outreach side, we work very closely with emergency managers up and down the coast through my counterpart, Dr. Althea Rizzo, who works for Oregon Emergency Management. And so we focus on 2 different elements. On the one hand is the mapping and modeling work that we do as an agency. And then on the other hand is the education and outreach. And obviously our collective goal is to build this culture of awareness about Cascadia, because that's ultimately what's going to save lives. That's a critical part of the work that we do. So in the timeline on the bottom there, you can see in blue past events that have impacted this particular region. Obviously beginning in 1700 with the great Cascadia earthquake, 322 years ago. And obviously since then, we've not seen any comparable activity on the subduction zone. And so that tells us that strain is already accumulating and it's building towards the next great earthquake, which could happen at any point in time. So in 1964, we saw one of the evidences of a major distant event impacting our coastline. Because of the 1964 Anchorage, Alaska earthquake. It killed, I believe, 4 people who were camping on Beverly Beach, caused quite a bit of damage in various ports and harbors up and down the coast. But on the whole, the impacts were actually fairly minor in the scheme of things relative to an event that would take place locally along our coastline. In 1995, the state of Oregon began developing the first regulatory maps for the entire coast. And the purpose of those maps were to really address concerns around critical facilities, basically the locations of schools and hospitals in the inundation zone. And so that regulatory line essentially precluded construction of new facilities in the inundation zone. And over the years, we've seen up and down the coast, a number of schools being moved out of the inundation zone. Classic example, obviously nearest to us, is down at Warport. And most recently, the Seaside High School up in the community of Seaside. So then we have the Sumatran event in 2004, which was really a staggering event resulting in about 204,000 deaths. And really that was the impetus for accelerating some of the work that's been going on around the country in regards to tsunami preparation. And it was a major triggering force for a pretty large capital injection to the tsunami program. And so it allowed us in 2009 to essentially develop the next generation of tsunami evacuation maps for the state of Oregon. And that was through a multi-year funded effort that lasted up until 2013 when we completed modeling along the coast. And so we now have today, obviously, evacuation maps and inundation zones that span the entire coastline. Prior to that, we were doing it at a rate of 1 community per year. So it would have taken us about 20 years to have completed the coast, which we were able to do in 2 or 3 years. So funding matters. Our focus since then, obviously, has been directed at evacuation modeling and maritime preparation, as well as risk assessments. So here's the regional setting. The image on the upper left there is a cartoon of the Cascadia subduction zone. On the left of that red line there is the Juan de Fuca plate. It's moving in a northeasterly direction at about 1.6 inches per year. And then on the right-hand side of that image in green is the North American plate, which is moving in a westerly direction. And right along the subduction zone, which is highlighted in red there, is a region where scientists have concluded that the subduction zone is presently locked, and so strain is accumulating. And I mentioned, obviously, in 1700, that was the last coastwide big Cascadia event. So what we see in terms of schematically down below is that as that strain is building, what it does is it essentially uplifts the coastline gradually. And then as a subduction event occurs, that strain, that compression that's been building up over time is released. And there's an instantaneous movement, upward movement in the water column, resulting in the production of a tsunami wave. And then obviously that travels both landward and seaward until it reaches the coastline. So the image on the right is a product of some work that Lydia Staish and others at the USGS have been doing, which is compiling a very comprehensive data set of various geologic data sets, including the locations of core facilities and things like that along the coastline. So this image really just highlights the seismicity of the region. And it's showing the locations of earthquakes greater than a magnitude 4.0. And so what you can see right away is obviously a lot of activity along the Juan de Fuca plate, along the transform fault there, which is highlighted in the dollar sign there. That's a little boo-boo. Obviously, when we transferred the PowerPoint, it didn't quite come across correctly. And those white lines are supposed to show arrows pointing in opposite directions, which is obviously a spreading ridge region. And so you see a lot of earthquake activity along these margins of these tectonic plates. But right along that solid black line, there's virtually nothing going on other than a few sort of crustal events and things like that. And so Cascadia is a very silent subduction zone relative to other subduction zones around the world. And that's why we're so concerned about obviously the implications from this type of event. So there are a variety of different data sets that we use to actually drive the modeling, and these can be divided into an on-land Paleoseismic record. These are very old geologic data sets. The evidence for this on-land record includes evidence of subsidence, where the ground has been essentially dropped instantaneously during the event. And this is highlighted in the image on the upper right there, taken from Benson and others in 2001, which shows a buried forest, just highlighted in that solid white line. That's the buried forest floor with a tree stump to the right of it. And obviously tsunami deposits and post-seismic sediments have accumulated above that since that particular event. So that's an example of a coast-seismic subsidence event. Other evidence includes tsunami deposits, where you can go into these various estuaries along the coastline. You can drive cores down, and you can actually find tsunami sands, and you can actually track those sand deposits in certain estuaries really quite well. Salmon River, for example, has a really tremendous record spatially within that estuary, and so you can get a sense of the inundation associated with those past tsunami events. And what you see is an upward finding of the sand layers, and then a landward finding of those sands going inland. And we can conclude from various data sets that these deposits were unlikely to be produced by storm waves or floods or other factors like that. There are also liquefaction deposits and landslide deposits as well that folks have been studying in the Pacific Northwest. So we can use these data sets to estimate both the rupture extent, but also the source areas for tsunamis. We can estimate the amount of subsidence for different magnitude type events, and then we can model these to look at things like the extent of inundation and also things like the movement of sediments. So how are these various layers defined from a geologic standpoint in terms of being able to define their ages? So we use a variety of different techniques, ranging from dendrochronology, which is looking at the tree rings and literally counting tree rings, which provides the most detailed and best measure of ages for these buried trees. We can also use radiocarbon, where we can actually date plants and vegetation that may have been trapped in that layer just above at that buried forest soil layer, where it transitions to tsunami deposits above it. The challenge with these types of techniques, at least the radiocarbon ones, is that there's often quite a large uncertainty. So there's a minimum maximum age, and that can be anywhere from tens to even a few hundred years. And so that presents challenges when you're trying to actually constrain the size of events and being able to relate events geospatially along the Pacific Northwest region. So there's also an offshore series of work that's being done, primarily being led by Chris Goldfinger and many of his students at Oregon State University, and essentially looking at deep ocean cores in submarine canyons and off the edge of the continental shelf. They're able to identify the occurrence of what we call turbidity currents, where these are large submarine landslides that are triggered by a giant earthquake. And because of the proximity and spatial distribution of these deposits along the Pacific Northwest region off that shelf there, and through, again, very detailed analyses of the dates of these deposits, one can really narrow down and refine the ages of the time series and be able to extend this data set going back almost 10,000 years now. So based on the work of Chris and others, what we can define is that for a full margin rupture event, we're looking at about an average of around 480 to about 505 years. So that's about average. So that corresponds to the 19 events that some of you probably have heard about over the last 10,000 years. And then there's evidence of other types of events having occurred with different distributions, ranging all the way down to the very southern Oregon coast, where we have a much shorter record, but evidence of much more frequent tsunami inundation events occurring down there. There's 26 of these smaller events which have a recurrence or an average recurrence of around 220 years. So again, keeping in mind that Cascadia last erupted 322 years ago, South Coast tends to rupture on average about 200 years, full margin ruptures roughly on the order of 500 years. But obviously within that data set, there's actually a lot of time differences between events ranging from as little as 100 years to as much as 1100 years. So geologists have compiled all these on-land deposit data sets, and I'm not asking you to read this. It's a very complicated, horrible slide. Actually, it's a great slide because it really shows the phenomenal record. This record that we have in the Pacific Northwest is really unprecedented in the world. And so it gives us great confidence in our ability to identify both these smaller events and big events along the coast. So essentially what this image does is it shows much higher frequency of events and very detailed chronological mapping of events in the last 5,000 years, 6,000 years. And that's really a reflection of these on-land deposits. And then the longer bars that extend well out here, these ones here reflect the product of turbidity current assessments by Chris and his team. And so that gives us our 10,000 year record. So again, we can identify these 19 events. We can identify various rates of return for different portions of the coast. And we can obviously identify that there's a lot of uncertainty with these data sets as well. So these data sets really form the foundation for the tsunami modeling work that we began in 2009. And the goal of this work was really to represent as full a range of plausible Cascadia tsunami sources covering all geologic, reasonable geologically modeled space, but while we're erring on the side of conservatism. So one of the things we did was, as part of our modeling, was that we used zero friction in our numerical models because the desire was to actually, because these map products were going to be used for evacuation purposes, we wanted to really be as conservative as possible. But reality is when you factor friction into a modeling exercise, you're going to reduce the size of the waves and the inundation extents. But we didn't want to do that. We wanted to make sure that we were actually mapping something as conservatively as we could because of concerns over uncertainty as to the geologic record. So the image on the bottom right there shows really the time history and then the classification scheme that was developed by my colleagues, George Priest and Rob Witter, which basically focused on using a t-shirt size classification scheme. So in dark blue at the bottom there, we have small events, of which there are 3 out of the 19. In purple, over here, we have our medium events, of which there are 10. We have 3 large events, 1 extra large event, and no XXL or extra large size event. There's some debate about whether there's actually another event in the geologic record that could be close to an XXL event, but essentially this is what we ended up landing with. So obviously the ones in blue and purple here, these are much more frequent events compared to these much bigger, more catastrophic scale events associated with large all the way up to XXL. So there are 2 approaches for actually modeling tsunami hazards. There's a deterministic approach where it's very much scenario based. So similar to what the graphic I just showed before, where you divide events up into scenarios ranging from small all the way to large to extra large. There's also a much more complicated and comprehensive approach, which involves probabilistically modeling all possible events. And this includes both large events as well as many smaller events. So at the time, the decision was made to focus on the deterministic approach, primarily because the modeling using a probabilistic approach was not well defined at the time. And it would have actually required the development of many hundreds to even thousands of potential earthquake sources to feed into that type of modeling exercise, and is just prohibitively expensive, at least at the time, as well as computationally quite demanding. So we took the deterministic approach. I'm not going to say too much about this, other than we utilize a variety of different earthquake rupture models. The most common one is what we call a buried rupture, as well as a splay faulting, where part of the actual fault movement is directed towards splay faults. These are additional faults that occur out in that offshore, that Pleistocene wedge area that's been accreted up against the continental shelf. And so it can actually trigger enhanced movement, because those splay faults are actually dipping landward in a much steeper fashion. As that earthquake ruptures along the coastline, it drives energy towards those splay faults, and it creates a much greater vertical uplift. And so it turns out, when you actually do the modeling, the splay fault scenario produces really the biggest tsunami waves along the coast. From work that was being done in Japan by Gower and others, a new type of rupture model, which was a trench breaching event, was identified, and was contributing to some of the large run-up elevations we were seeing there. It turns out that in Oregon, when applying this particular approach to earthquake modeling, it doesn't actually produce as big a tsunami along our coastline, primarily because the geology of our offshore shelf is so vastly different to Japan, and because of our less steep offshore shelf and wedge area, it just is unable to produce the sort of comparable size tsunami events as we saw in Japan. So we can put this all into what we call a logic tree in order to parameterize all the different parameters, and then develop the various deterministic scenarios. We incorporate the coastseismic response. This is from the geologic data that's derived on land that define the degree of subsidence that occurs during these events. And so this is largely based on work that's been done by Andrea Hawkes, Rob Witter, Harvey Kelsey, and many, many others. And we use those alongshore subsidence data to then scale up to our 5 deterministic scenarios, reaching up to the biggest one of XXL. And so you can see out here, so on the central Oregon coast, we would expect to see around 1 to 2 meters of subsidence, with about a small to medium size event, even up to a large. But obviously, as you scale up to an XXL, we're looking at sort of 2 to 3 meters. And as you go down on the south coast, we see even larger coastseismic responses down there. So, up to 5, 6 meters. There's a lot of work that's being done over the last several years to try to better refine this. And so looking to the future, we expect to see further refinements of this type of deformation along the coastline that will probably be part of the next generation of earthquake source models. So what does this look like at different locations along the coast? So what I've done is I've taken a transect at 3 different locations, one on the north coast, one in Newport, one down by Gold Beach. The bottom plots show the actual deformation associated with those 3 different rupture models. And then the plots above the deformation plots shows the actual generated water level out in the ocean. And what you see is that the splay fault model, which is in red here with the abrupt peak, which is really dominant in this northern part of Cascadia, produces the largest tsunami. And so based on this data set, the decision was made in consultation with emergency managers that we would use the splay fault model for all evacuation purposes. And so some people refer to as our XXL1 or M1 or L1 type scenario. So that relates to the splay fault model. So the end result is you can summarize all this data. We can highlight the various characteristics about these different events, ranging from obviously in magnitude, an 8.7 for a small, all the way up to a 9.1, which is our XXL size event. The key thing here is obviously the differences in the amount of slip associated with these various scenarios, ranging from a 10-meter amount of slip, 18 for medium, which is very similar to what scientists believe took place in the 1700 event, and then scaling all the way up to around 40 meters, almost double what happened in 1700 for an XXL, hypothetical XXL size event. And you can see run-up elevations ranging from obviously very small for a small event, all the way up to 25 meters or around 70 plus feet for an XXL size event. And obviously that varies spatially along the coastline. So this image here really tries to, demonstrate or capture the along coast variability in maximum water levels at the shoreline, so actually at the coast. So on the left side here, we see the small scenario. On the far right-hand side, building all the way up to that XXL scenario. And so you can see right away elevations with small at the coastline of around 15 to 20 feet, increasing to on average around 50 to even 70 feet for an XXL size event. And obviously you can start to see on the very southern Oregon coast, very significant run-up occurring down there, a product of the wave propagation into the Rogue Canyon and amplification along the coastline there. So how long can we expect the earthquake shaking to last? So this is a graphic that was derived by Allan in 2011 following the Tohoku event. And so on the left is the seismic moment, and then on the right, on the x-axis along the bottom there's time. And so in red you see the Tohoku event, which is characterized with a time of around 2.5 minutes of earthquake shaking. Whereas the Sumatra event, which is in black, 600 seconds, is close to about 10 minutes of earthquake shaking. So based on assumptions about the length of the Cascadia fault line, as well as other factors, we can estimate that the degree of shaking that we might experience would be somewhere on the order of about 3 minutes to maybe as much as 5 or 6 minutes. In reality, if you have smaller events that relate to only partial ruptures of the subduction zone, that degree of shaking obviously decreases quite a bit. But in general, we would probably expect to see anything over about a minute for a major subduction event, extending all the way up to 6 minutes. So just a reminder of what we can expect to see. This is from Tohoku, Japan, being an analog for Cascadia. So obviously the upper image there, the Miyagi prefecture, showing the scale of the tsunami coming in across the plains there. In some areas overtopping trees out along the coastal strip. The bottom image is an amazing shot of the tsunami inundating the community. You can see lone bridges there that obviously would have been important at the time for evacuation purposes. Obviously, we were able to survive the earthquake. And then obviously in the right-hand side of the image there, you can just make out I believe this is the Sendai airport. More carnage up on the right-hand side. This is a disaster management building. It's a very famous photo of the degree of inundation. I believe the mayor of this particular community survived by actually climbing up the telecommunication tower up here. I think there were 3 people who actually survived in this particular location. This building housed about 250 people. And so this is really a testament to the magnitude and scale of the disaster. And obviously, from our standpoint, what we need to be mindful of. So how are these data sets being used? Well, used obviously in many different ways. For developing evacuation maps and brochures that can be used for both individual as well as community preparation. These data sets are being distributed by web as well as obviously hard copies, but also now we're moving towards getting more of this information onto smartphones. Some communities have adopted our tsunami inundation maps for planning purposes. So these are referred to as tsunami overlay zones. So some communities are using, for example, a large inundation zone for mitigating against construction of certain types of critical facilities. Others are using XXL, and still others are using even older older inundation maps that were developed in the early 1990s. So there's kind of a mixed bag in that regard. The maps are being used for facility improvement planning, so particularly for retrofitting bridges, as well as for obviously input in towards developing vertical evacuation structures. And then communities are also using this information for mass care planning. So we can actually go to the next level and start to do risk assessments and look at the potential for casualties, the potential for the displaced population, things like that. And those data sets can then be used by emergency managers to build their caches and develop their plans for how to deal with post-disaster planning, such as sanitation and dealing with food supplies and things like that. We've done a lot of work with our outreach, helping communities establish signage. These are blue lines that we started installing along the coast in 2013 that basically define the location where you leave the inundation zone and reach safety. We work closely with the Seaside High School in this example, and we're able to fund them a lot of the signage that they've established in the community of Seaside. And then up here, we've been moving towards obviously putting more and more of this information into web-based activities. So in the last few years, we've focused a lot of our attention on evacuation modeling. The purpose for this was really based around the idea of, as a community, we kept receiving questions about, how much time do I have to get out of the inundation zone? Where do I go? And how fast do I actually need to travel to get to high ground? So when I first came on the coast here, it was not uncommon to hear about people practicing walkouts and drills. Well, it turns out that walkouts may not be sufficient in some communities. You actually may need to be doing jogouts or even runouts in order to get to high ground in time. And that's because in some areas, the tsunami arrives very, very quickly relative to others. And of course, some people may be located further away from safety compared with others. So this has been a major focus for us. The other important thing about this type of modeling is that we can actually account for the potential for bridge failures. So for example, this is Seaside in the middle of summer. You can see many hundreds to several thousand people out on the beach here. This is a volleyball tournament that's going on in peak summer. And so you can imagine a situation where Cascadia were to happen. How are you going to get all these people out of the inundation zone quickly enough and with minimal loss of life? And recognizing that 3 bridges in that particular community are expected to fail because they haven't been seismically retrofitted. And so these types of data sets can really help drive the guidance on being able to retrofit these bridges. So lots of different inputs go into this. Obviously, things about information relating to our roads and our trails. We need to know the evacuation zone, so we use XXL. We need to have digital elevation models that capture the slope and distance, which comes from our LiDAR data. And then we also need to know the wave arrival times for any location in the inundation zone. And so we can plug that in using a technique called least cost path distance modeling, which is a technique built into ArcGIS. And we can begin to generate maps like this. This is an example for Cannon Beach. And so here we see on the left is our base run, where we expect the bridges there across the Cola Creek to fail. And so you can see in pink there, up in this part of the downtown Cannon Beach, anyone located in this area would actually need to be moving at a jog speed in order to get to high ground in the south here. And obviously, as you get closer to high ground, it transitions from jog to fast walk to slow walk. And then similarly on the north side, you can see most people can actually get to high ground fairly quickly. So then you can start playing with various simulations where we can actually retrofit the bridge. Now we can allow people to cross the creek there, and you can see very quickly how conditions can change. And so people in downtown Cannon Beach could potentially get to high ground on the north side here much, much more easily if the city were able to actually get these bridges retrofitted. And you can play similar sort of games with by putting in vertical evacuation structures in our various communities. So we've actually done this for every coastal community along the Oregon coast now, except for two, being Depot Bay and Toledo, because they're further inland or are less exposed relative to other coastal communities. The goal will be to eventually obviously finish those two communities as well. So working through with the collaboration with University of Oregon, the infographics team there at the Department of Geography, we were able to then take our evacuation modeling results, and through a technique called network analysis, network road analysis, we can take those path distance speed results and turn it into actual routes that can be queried on the fly through our Tsunami Evacuation portal. And so this is an example for downtown Seaside, where you can enter a physical address up here, or you can click anywhere in the inundation zone. It'll automatically generate a route for that location, directing you to the nearest point of high ground. On the right, it displays the actual turn-by-turn instructions, and then a recommended speed. This is really the minimum speed that you need to be moving in order to get to high ground in time. We also provide the walk speed and obviously the run speed as well. But this is the speed that you need to actually maintain in order to get from this point out here nearest the ocean all the way to the nearest assembly area or high ground point in those eastern foothills. So we've actually been able to do this now for every community along the coast. You can go to our nanus.org site, bring up the Tsunami Evacuation web portal. You can dial in any address along the coastline, and it'll be able to provide you with this type of information. So if you come across problems or you see things that look weird, do let us know. So the next part of the work that we've been doing is really focused on developing these risk assessments. And the goals here was to obviously identify numbers of casualties, both fatalities and injuries, because that's critical as part of your pre and post disaster planning. Assess things like building losses and debris volumes. And then obviously we can also begin to assess economic impacts. So how do we do this? We look at basically what's in the inundation zone in terms of buildings, both usage and types. We could look at people, where they're located. We can look at ages. We can then input the earthquake parameters. These are the ground shaking models based on the underlying geology, which means we can vary the degree, or rather the models vary the degree of shaking intensity based on whether it's on rock or fill material or sandy deposits and things like that. And that has a direct bearing on whether a building may survive or could fail in an event. We then bring in the tsunami inputs, and then we can do the analysis using a technique in Hazus, and generate these loss outputs. So we can do this for different types of parameters. So this image here on the left shows the inundation zone in yellow. All those little red dots along the coast here, although you probably can't see them as dots, but they're kind of merged together. But all these represent buildings, individual buildings. So we can then assign populations to those buildings based on their usage. We can then start to calculate potential for casualties, and we can generate a plot like this. So this graph here is the percentage of fatalities by community for the three different tsunami inundation scenarios that I'm using here, which is medium all the way up to XXL. And so we can start to see right away certain communities really start to jump out in terms of having major challenges. So for example, Gerhardt is not really impacted by a medium or large size event, but as soon as you get to XXL, then it completely inundates that community. And because residents there have to travel 2 or 3 miles eastward to get across 101 up into those eastern foothills, it makes it very challenging for people to survive. And so we see potentially a large loss of life in a community like Gerhardt. So this means that, for Gerhardt, they probably should be really thinking about vertical evacuation structures as a means to try to reduce this potential risk here for that community. Similarly, in Seaside, we can see potential fatalities reaching 60 to 70% of the community based on these different scenarios. And again, vertical evacuation structures or even retrofitting roads may be a solution to mitigating this particular problem. And then we can do the same thing for other communities up and down the coast. I think the point to take from this is that we can clearly identify those communities that are really most at risk. But what you also see is that there are many, many communities up and down the coast that are actually where the potential fatalities are much, much lower, typically in the 5 to 10% range. And that's really a function of the fact that we're actually very fortunate here in Oregon in that high ground for many of our coastal communities is actually really close by. And so you can get to high ground pretty quickly. And that's obviously a real plus for us. I'm actually going to skip these last two slides because I'm running out of time here. I guess one of the take-home messages from this type of risk assessment is that we can then start to play games by changing the speed at which people move. We can change how much time people spend before they actually start to evacuate. So there's this departure time on the x-axis here. So we assume for all our evacuation modeling that it's going to take people about 10 minutes before they get going. So that includes around that 3 to 5 minutes of earthquake shaking and about 5 minutes to grab their go bag, get out the door and get moving. So it's actually not a lot of time. And so we can account for that. And you can see very quickly, just by increasing your travel speed from a walk speed to a fast walk, we can actually really start to save lives. And from an emergency management standpoint and communicating to our visitors, et cetera, this is really very important for people to understand. So know where you're located in the inundation zone and know your route and move as quickly as possible. Don't walk, run, jog, run, that type of thing. I'm actually going to skip through maritime modeling because I've only got a few more minutes, but that's been another focus. I wanted to just finish up with this last slide here. So what I've really been speaking to is work that we've been doing over the last 10 years based on these deterministic modeling efforts. So at the national level, there's been some significant movement towards developing more probabilistic-based tsunami inundation modeling, both here in the Northwest, but also elsewhere around the country. And so back in May, I was part of a team of researchers, scientists from the USGS, as well as various universities in the region and extending all the way up into British Columbia. And so the goal of this meeting was which was being hosted by the USGS Power Center in Fort Collins, was really to bring together the best available science that we know about subduction zones, and in particular Cascadia, and begin to develop these next generation logic trees that would essentially guide future development of tsunami inundation modeling and potentially changes to our evacuation maps or for other types of purposes. So we had a really outstanding meeting. The end result is a new generation of earthquake sources that will be developed over the next 2 years, and then leading to new modeling that will probably start around 2026, that we hope to complete around 2028. From the standpoint of the modeling side, because it takes such a long time to produce these maps, we'll probably have to do this in a phased approach, focusing on the North Coast first, and then at a later date, we'll then shift towards trying to complete similar activities on the South Coast. Obviously, from our standpoint, this allows us to actually put our deterministic sources into a probabilistic framework, and that's really important as we go towards designing buildings such as this. This particular building was designed to withstand an XXL size event. And so that's really good because the tsunami where we are here is estimated to be about a 12-meter wave as it flows through here. And so obviously you need to be able to design buildings such as this to withstand the types of forces that would be hydrodynamic forces that would be impacting the building, but also to address things like ballistics from fishing vessels that are moored in Yaquina Bay here that could be picked up and carried inland, or the major cruise ships that may be parked at the NOAA facility here etc., or vehicles and that sort of thing. So we need to actually be able to account for this type of work as part of this probabilistic modeling exercise. So I'm going to stop there. I'm not going to read through this. You can read through that in your own time, but I'm happy to take any questions. I apologize, it took a little bit longer.
Thank you so very much. So I'm going to start with questions online. Do we have any?
We have several questions online.
Can you start with one of them, Roseanne?
Yeah, the first one is a special effort being made for telling tourists where to go?
So that's a really excellent question. It's one of the challenges for us. So we know our resident population, and we can make estimates about the potential effects of Cascadia in terms of loss of life and things like that on the resident population. But it turns out it's our visitor population that's what we really must worry about, because reality is many of these folks come into our communities and really don't understand that, A, they're not familiar with the hazard, or they don't understand it, or they don't do due diligence and learn about evacuation maps, or perhaps just simply are familiar with the types of products that are out there to find evacuation routes, either online or through paper maps. So it's a challenge. Jenny can speak to this, probably Jenny Damaris, who's the Lincoln County Emergency Manager here, who's sitting up the back. She can speak to this probably better than I can. But this is an enormous challenge for all emergency managers up and down the coast, is how we actually convey this information to our visitors.
Questions in the room? Hang on 1 second. 1 second.
Does a mega earthquake off our coast guarantee a tsunami?
Yes.
A question online.
Okay, did I hear you say you put a 5-minute buffer into the walk, jog, run time estimate?
Yeah, so what we do is and I didn't speak to this earlier, but so we factor in actually a 10-minute delay into our evacuation modeling. So we account for about 3 to 5 minutes, which we estimate is what the earthquake shaking could take for a big event. And then we factor in an additional 5 minutes for people to get themselves organized and get underway. And it turns out that's actually not an unreasonable estimate. So about a 10-minute delay, it's not unreasonable, because it's been found from various surveys that have been performed in other parts around the world, that Nicaragua being one of the examples, where they found that it took people about 7 minutes to get going. So we decided to be a little more conservative, factor in 10 minutes, and we take that off the available time. And so what's left is what we use, or what we define as the time required to get to high ground.
All right, questions in the room. I thought I saw another hand. All right, each one, hang on just a second.
Great presentation. A question about, you had mentioned friction and not accounting for friction in your modeling, and then having a conservative rate of I guess how high and how fast. I'm wondering, do you have any information, or can you elaborate a little bit more on friction and the impacts on how fast and how high a tsunami wave would be?
So it depends. We have done simulations in various locations up and down the coast where we model with friction and without friction. And it can actually make a very big difference, but it really does depend on where you are. So let's say if we speak to Seaside, for example, Seaside is a broad plain backed by sea cliffs on the eastern foothills side. And so the difference between a zero friction scenario and using a Manning's N that we use of about 0.025, which is akin to a sandy substrate. The difference between those two and the inundation extent there is negligible. But we can go to somewhere else like Brookings Harbour, and the differences can be actually quite substantial. And so, meaning that when you incorporate friction, the inundation extents will be reduced, generally speaking, and the current velocities or the current velocities that are generated as part of the tsunami are also reduced, which means that the energy when designing buildings like this is also reduced. And so you can factor all that into the design and so on. Does that answer the question? Yeah.
So the question is about centric to Newport. Do you have any comments about Newport?
Yeah, so actually the community of Yachats contracted with our tsunami modeler to look at the effects of friction and no friction scenarios down in their community because they were wanting to design, they're wanting to build a new fire station. And so locally down there, it actually made a small difference. It basically allowed them to build at a lower elevation relative to XXL. So it can vary. Locally here, I can't speak to that because we haven't actually done that particular modeling, but it varies substantially up and down the coast from negligible impacts to quite big differences.
Okay, back to online. A question online?
Yes. What is the tsunami modeling software used? And if we want to collaborate on research in evacuation modeling, what should we do?
So we actually work with a colleague at Virginia Institute of Marine Sciences Center, Joseph Zhang. He's a professor there. He's developed his own tsunami inundation model called SCISM. There's a number of different types of models out there. I think there's at least 20 that I can think of that have been utilized over the years. All the numerical models that we use or NTHMP member states use must be benchmarked. So again, there have been protocols that have been developed for modelers to actually test their models against existing data sets, as well as both physical models, as well as wave tank models and numerical simulations. So they all go through a very comprehensive benchmarking exercise to validate the models that they're producing, the right amount of inundation and things like that, and replicating real world examples well. So SCISM is what we use. There are various other types out there, Geoclaw and MOST and various other things. In terms of collaboration, I mean, I would say reach out to myself initially, and I can put that person in touch with Joseph and others if you would like to explore other types of tsunami models.
Great, thank you. Question in the room. Okay, hang on.
I was looking at the building loss modeling, and there are some sparsely populated places that had relatively high building losses. I'm thinking specifically of Tillamook County compared with Lincoln County, which Tillamook County lagged a little behind Lincoln County, but significantly fewer people in Tillamook compared with Lincoln. And is that a function of the real estate values of the buildings that will be lost? Or is that a function of what those buildings are built on? Or some other function?
So it's probably all of the above, i.e. it's a function of, these losses are based on what the underlying geology is. So if it's on liquefiable soils and it's a wood frame construction, it probably could survive a large event. If it's a unreinforced masonry building on liquefiable soils, it's probably going to collapse and fail. So you look at things like that. Obviously, that's the earthquake side of it, and then the tsunami side of it. You know, anything in the inundation zone is going to be severely impacted. We know that most of the buildings located in the inundation zone are wood frame construction, and so they're just not resilient to a tsunami. So that would be, those are the various factors that go into it. Differences between Tillamook and Lincoln can also be accounted for by the fact that, Lincoln County has large areas of development that's built up on marine terraces. Most of our communities are out of the inundation zone. Whereas in Tillamook County, you can look at, Rockaway Beach, Noddle Beach, Netarts, Cape Mears, Nesquin, Pacific City, they're all in the inundation zone. And so those would probably account for differences as well.
All right. Any more questions online?
Yes, we have a few questions.
Okay.
One is, how are tsunami zones and evacuation routes being communicated to residents that don't have strong science literacy? Maybe use a language other than English or have other communication barriers.
Okay, yes, I appreciate the comment. That's obviously a challenge. So what we have tried to do is produce as many different products as possible that can actually assist individuals make the decision themselves or have access to information products that can help them make a decision about whether they're in an inundation zone or not. We actually, with our Beat the Wave evacuation maps, we worked with the infographics team. And so they had a lot of expertise in trying to remove a lot of the sciencey jargonism out of our brochures and really scale it down to what it ultimately means for most people. And so that was actually a very useful exercise to really try to really refine some of those types of products. So we can do things like that. I'm not sure, did I answer the question effectively?
Pretty much, yes. A related question is, on the fly maps on a smartphone assumes that cell towers are functioning after an M9 earthquake. Wouldn't posting more signage for evacuation routes be more reliable?
So keep in mind that any of our products, maps, online tools, etc., are really all designed for pre-disaster planning. This is what you do before the event. You need to know this information. You need to know your routes. You need to know where to go before the event happens. You're quite right, absolutely right. Our cell phone towers will probably be down, and you will not be able to access this type of information online. And quite frankly, you shouldn't be accessing this type of information online. You should know that information beforehand and be able to respond accordingly. So in the case of Cascadia, along our coastline, most of our communities actually don't have tsunami sirens. And there's a variety of reasons for that. But one of the things we want to try and emphasize is that on our coastline, the earthquake shaking is going to be your warning. Keep in mind, you've got 3 to 5 minutes of earthquake shaking. And I would recommend having a look at some of the videos that came out of Tohoku, Japan. It's really is quite startling how long a time that is. And so that's your signal that a big event has happened. Anything over a minute is probably Cascadia going off, or at least parts of it. And that should be your signal at that point to drop, cover, hold, and then evacuate as soon as the earthquake shaking stops, or if you're outside, evacuate as quickly as you can and get to high ground as fast as you can.
Okay, with that, I'm going to go ahead and call time on this. I know there's some folks that are online. Please hang on and we'll try to answer your questions. For those folks in the room, if you have additional questions, maybe John will stick around for a few more minutes and we can answer those. I also just want to promote the fact that we are doing an evacuation drill in this building on Friday at 12:30 in the afternoon. If anybody's interested, you're welcome to come walk up the outside ramp and see what the materials are we have in our emergency cache up there. Everybody is welcome. The other thing I wanted to say is if you haven't noticed on that ramp, if you haven't walked it yet or you haven't noticed, there are the t-shirt size markers in little metal strips. so you can actually walk them and know what they mean now, because we don't have signage on them yet, but you learned about that today. So just wanted to share that. Before I let everyone go, let's just thank John one more time for spending time with us. Thank you.
Thank you.
All right, everybody, we'll see you next fall. John, can you kind of come over and maybe answer a couple of those online?
Sure. I turn this on.
Oh, keep it on. That way you can just talk to them.
Okay, we have a question. How safe do you think our vertical evacuation building is here?
I think it's very safe. This particular building was designed to withstand our XXL scenario. So it's actually well exceeding what's actually required by American Society of Civil Engineers. And so I think they've done a remarkable job.
Okay.
But I'm not an engineer, so I'll defer to the experts on that one, but that's my understanding.
A second part of the same person here said, will most people be able to leave their homes after the earthquake? How likely is it people will be trapped in their homes?
That's an excellent question. It depends. So, for example, folks living in manufactured homes may experience difficulty getting out of buildings if there's been substantial movement off foundations and things like that. It's quite possible that obviously older construction, anything that's really constructed pre-mid-1990s, there's significant risk of failure or significant damage. Anything that's post-1996 and certainly even post-2005 is more likely to be built to much higher seismic design standards. And so those sort of challenges are less likely. But this is always going to be an issue.
Okay. One question. So if the quake is offshore and not felt on land, would it still generate a tsunami?
That's a really excellent question. So this is a topic that's been of interest in that there's potential with these smaller partial ruptures of the subduction zone on the south coast may result in no earthquake or no felt earthquake shaking, say for people north of Newport. It turns out actually probably people north of about Newtarts. And so for them, it's almost like a distant event if you're up in, say, Seaside for one of these smaller south coast events. So that is one of the challenges, but in reality, for a full margin Cascadia event, people will feel the shaking.
Okay, and one last question. Are hotels required to have these maps and information?
Jenny, I believe some communities do and other communities don't. It varies. It's not statewide.
Okay, that's the last of the questions.
Okay, thank you.
Okay, thank you.
Now you can turn off. For everybody online, thank you so much for being here. We'll see you in the fall.